Hi, I'm Micah Weston. I'm a student in Dr. J. Marpaung's embedded design course, and I will be presenting the final project where we had to use Verilog hardware design to interface with a keypad that would control LED incrementing on the board and the speaker, while also having a 7-segment display scrolling a message at a constant rate. So to start off, I'm going to switch cameras to show a demonstration of the project.
All right, as you can see, this is the board demonstrating. So to start off, we just have the simple scrolling display that shows my name on it scrolling through, and then it shows fall 2020. I decided to go with single digit letters for each one, even though I have some wide letters such as M and W, keeping it to a single digit so that you would see each letter on a single display ended up helping to more easily read the display. And now we have the keypad up here as well as the display. So if I press, for example, 1 on the keypad, you'll see that the LEDs have added to 1. And then if I press 2, that ends up adding to 3 in binary. And then we can press A, and that will add to 10. And so that ends up being there. And then with each button press, you can hear a sound coming through and updating. Sometimes the keypad, the membranes are a bit difficult to bounce back because they kind of indent and you have to kind of push on the back. If it was more securely held down, that might be less of an issue. And that's the basics of the project. It just has the scrolling display, the LEDs that update with each increment, and then the keypad controlling tones on the speaker.
In this section, I'm going to walk through the RTL viewer generated output from Cordis Lite that shows the schematic that was generated from the Verilog code. So there are 2 main submodules, a rotating display submodule and a keypad with tones. Starting off with the more simple rotating display, all it takes in is the clock signal and puts out the 6 outputs. There are 7-bit outputs for each of the 7-segment displays. Within it, we have a timer submodule that just takes the clock signal and basically reduces it down to 1 second rather than 50 megahertz. Inside, it just does this with a comparison, and then a D flip-flop register that counts up using this addition sign until it's equal, which will show pulse the output. And then it will also reset the timer down to 0 using the multiplexer over here. That gets fed into the automatic main display, which ends up driving a state machine over here, and also the registers that hold the outputs for each of the 7-segment displays. So for whatever reason, Cordis decided that the register for the first display, which ends up getting updated by the progress machine processed through all these OR gates, is actually split into 4 registers here. So there's 2 1-bit registers, a 3-bit register, and a 2-bit register. And then the remaining registers are each 7-bit D flip-flops that end up being used for the other 5 display outputs. And the way this ultimately works is basically like a bucket brigade, where they pass off their outputs to the next register with each clock cycle. So the first register combination updates the first register, or the second register, which ends up updating the next one, which feeds through and updates the next, and it works pretty much like a bucket brigade. And that's how the automatic scrolling display works. And then moving on to the keypad with tones, which is much more complicated. It ends up taking the keypad rows as inputs and then has outputs for the keypad columns, the signal out, as well as the LEDs. And so inside it's quite big. Where it really starts off is with the keypad processor, which basically just reads in the value of the keypad, ignoring any sort of debouncing. One of the main focuses I did in development was keeping each submodule to a very specific single responsibility. So this is why I didn't want to combine the switch debouncing with the processing of each row, because each of the buttons on the keypad are read through only 8 wires. So in order to do that, you have to cycle through each column, grounding out a single column and then reading in each row. And that's what ends up happening with this state machine. And then coming out, the 16-bit keypad signal gets fed into 16 switch debouncers that each individually debounce a signal. So I'll open up an individual one here. And what it does is it has 2 samples and then a timer to delay in between the samples. This gets compared to check if it needs to switch the output based on what's happening. The other nice thing about the switch debouncing is it also inverts the key value. So since there's a pull-up resistor in the button, it has the unpressed state as being 1, but now when the unpressed state occurs, the output will be 0 since it gets inverted in here. That goes into a submodule that parses the keypad. This basically determines what button is being pressed and if only a single button is pressed. So if multiple buttons are pressed, the signal displaying if it's pressed will not occur, and then keypad will default to 0. And also, depending on the key, if it's 1, the keypad number will be a 4-bit representation of 1. If it's A, it'll be a 4-bit representation of 10. And that ends up driving the other submodules that control the speakers here, and then also the LED incrementation. So with the speakers, it goes through tone data. Tone data is a combinational circuit that just decodes the 4-bit number back into 16-bit, and this determines each bit in a 16-bit count low number. That's how the timer counts the frequency inside of tone processor. So moving over to tone processor, this ended up getting taken from an earlier lab, and it just takes in the count low signal and flips the signal each time it counts up, very similar also to the timer submodule that occurs in the automatic display. So then moving out, the most difficulty I had was actually with incrementing the LEDs. Now, the module is quite simple. All it does is it updates the register on a edge of a signal, and it updates it based on adding in a certain value. This was quite simple. However, figuring out how to pass in the signal in order for it to propagate properly, I ended up needing to update it on the negative edge because that is the only time that the keypad signal would propagate through. So that all these combine together to produce the output that you saw in the demonstration before and create all the proper hardware design that we needed for this project.